All right then. So now you have our second presentation, and it's Subhan, our colleague, and then I think like it's a pleasure to have you here presenting, and I'd like to introduce like I tell you that this is we met personally in Aalborg when I was trying to I visited Petar, and also I met Sohan in there with Daniel and Arthur, and well, it was 3 days before COVID basically, and then we moved online back, and now you are here after some, let's say, few challenge years, like a 1.5 year probably, and then we are here. Like it was very good. One day we meet and then we start collaborating, and then we have a lot of things going on together, and this is one of the new things that we're doing, and then it's very promising results, as you're going to see. It's also related to fireman projects, and yeah, and that it's so Sohan and probably Pavel, and I don't know if Alex is also here. So these are some work that we are doing together for like a few months from now. Yeah. All right, so floor is yours, Sohan.
Yeah. Hey, thanks, Pedro. So hello everyone, and I guess I know a couple of you, maybe more than a couple, since I've been working with them. But yeah, so the topic is more about cybersecurity, which is a big issue in cyber physical systems. But when it comes to a specific Powertronics systems, there are multifold challenges, and for us, it's the problem of how fast your solution is, because Powertronics are naturally quite responsive tools in that way. So then when we talk about cybersecurity, there has to be a hypothesis. There has to be certain modeling principles. And based on the dynamics of the physical system, these hypotheses has to be derived in a certain way. So for Powertronics, we have our own hypothesis and other things, which I'm going to discuss, and what we are basically doing in fireman. So I'm not really going to touch base upon a lot of results, but tell you or introduce you more with the features of what we are doing and what was the challenge before we started this activity in fireman. So yes, I'm Subham Sahoo, and I'm an assistant professor in the Department of Energy in Aalborg University. AAU Energy, so our department has a lot of different systems, power systems, Powertronics, machines, fluid power, thermofluids, and all these things. And if you look at some of the theme-based research areas or research groups, it could be wind power systems, offshore, PV, microgrids, and then when you come to, this is all for Powertronics, and when you come to power systems, could be fuel cells, energy harvesting, thermal design as well, but this is more like a multi-vector system. So right now we are pretty much around 60 faculty members, 100 PhDs, and all these things. And we are doing quite good also in terms of ranking. So we have a new testing facility, which is a national testing facility for reliability of Powertronics. But we are not really looking into the reliability only, the reliability of Powertronic devices, but also the reliability of cyber layer as well. And that's where we are talking a lot about data and how this should be processed for Powertronics. So when I say Powertronics, I think I need to give a bit of background. This is more about energy conversion unit. So you can see that there are a lot of these devices that you're using today, and a lot of sources that you get your power from. And as we are moving more towards the green transition, these sources are always going to be dominating in the future. And then the device, which is actually responsible for delivering this into a standardized power requirement or standardized voltage platform, which could be 230 volts or maybe 6 kV or maybe 11 kV, based on if you're in the distribution level or in the transmission level. So when we talk about energy, these energy system is basically can be compounded into 4 different sectors, which could be production, distribution, consumption, and control. So production is, of course, production of energy at the the elementary level, and then distribution of power will be among here. So this is basically in the distribution level. Consumption, of course, if there's a Powertronics devices connected to all the appliances, that is the electronic loads, the consumption pattern is going to vary from, you know, just the normal appliances that you have, let's say impedance-based load and all these things. And of course, these things needs to be controlled finally, because you need to extract maximum power from these renewable energy sources. So as you can see that some of the inputs here are, well, solar irradiation, temperature, wind speed, and then communication as well. So all these converters basically need to talk to each other to see what they're doing right now. So if, let's say, if this converter is overloaded, they can actually talk and, you know, come up with a decision that, okay, we would like to reduce the overloading on this energy conversion unit, because in the long run, let's say if I look at 20 years, it affects the reliability. So if the lifeline of this you know, energy conversion unit is somewhere around 20 years, and if you're overloading it for a very long time, then that damages some of the power components, that is, you know, in this case could be IGBTs or MOSFETs. So when these components are actually degrading, the lifeline actually reduces by maybe up to 5 years as well, depending on how you use it. So then what you do is you take some of the overloading factor and distribute it among other things. So this is where the control is, and it can be centralized, it can be distributed. So there are many ways in which this can be, you know, handled. So net annual shares, as you can see, until the year 2018, renewable energy sources have actually grown across pretty much all countries of Europe right now. And this is where we need to understand why cybersecurity risks for our system has actually gone up. So as you can see, modern grids require health monitoring of equipments. It's not just only on the converter level, but also on the system level as well. And then we need to do some kind of monitoring of equipments, and then growing facilities as well. We need to do ancillary services. So we need to provide support to the grid. So we need sensors, data processors, and communication to do this. And then Powertronic converters dominating every energy sector. So of course, when you are coming up with a lot of ICT facilities, cybersecurity risks are bound to go up. So the issues of digitalization. So I think this figure will make it very clear for you. So if this is the physical system, and the cyber layer pretty much becomes the brain of the system. And if someone is trying to compromise any of these units, you know, or the nodes or anything like that, then whatever you are sensing from here, you're always going to, you know, end up with falsified control commands, and that is going to affect the system. Now, each of these units, each of these square blocks, as you can see, are Powertronic units, and you can see that they are communicating among each other. So there are many grid supportive services which are required from them, which could be grid frequency control. If you need to provide, let's say, voltage support, so that in that case, you need to send in reactive power, voltage or frequency regulation. So that is something else. If you need to dispatch active power to actually you know, regulate the frequency of the grid sometimes. So this is where it actually becomes vulnerable. All the cyber attackers tend to attack this part, and this is something which is, you know, a lot of people are still trying to do a lot of research on this. And this is not really very straightforward, because when I look at research in power systems, they are pretty much dependent on an observer-based approach. But we can't do that, because in Powertronics, which is basically why we started this collaboration with firemen, is because these faults or any kind of abnormal events are actually very fast. So in that case, if it's a cyber attack or if it's a fault, you can't really know, because you have to figure it out within 2 milliseconds or 1 millisecond. So how do you figure it out? So increased digitalization leading to advanced monitoring, diagnosis, control facilities. These are the good things. Grid supportive services, but increasing the vulnerability to cyber attacks. So this is where you can see that your brain can be affected in many ways by an adversary. And wrong use of data could lead to a lot of things: data theft, strategic data manipulation, false alarms, and disinformation. So these are some of the common attempts a cyber attacker could try to do in this case. So when I say cyber attack, what should you understand just for this presentation? A cyber attack is a third-party exploitation conducted in an illegitimate manner by injecting either false data into multiple or single sensor communication links or actuators, or by denying information from single or multiple sensors, communication links, actuators, with having a capacity to disorient the system objectives or goals. So some of the prominent cyber attacks that has already happened in the power grid are these three. So that is false data injection, man in the middle, and denial of service. So a very basic understanding, when you actually inject a false data on top of what your sensor is reporting. So this can be done in many ways. One could be the sensor acquisition layer, where you have the calibration gains, and you also have the control input. So let's say you're trying to provide a reference for the controller. So if you inject a false data on top of this, the controller is actually going to misbehave. So you are pretty much in a single node, and this is happening for the false data. So if you have access to multiple nodes, you can do that for many converters, and you can come up with a very bad response for the system. And then the man in the middle attack, because all the controllers are trying to communicate, and someone stands in between you and intercepts a false data. So if you were reporting 230 volts for one converter, so someone comes in and adds the false data on top of that value, or subtracts whatever they want to do, and this controller will receive a false information, and that's how the system will start misbehaving. And then you have denial of service. I think these are a few things that you might have heard already. This is also interruption. So you are, except for the fact that you are injecting false data here, you will interrupt information completely. So now the cyber graph is actually affected in some way. Okay. So cyber attacks in the last decade, you can see that there have been many cyber attacks on power grid, basically 2010, 2012, and actually one of the biggest cyber attacks that happened in Ukraine, in Kiev, where a lot of substations were affected, basically disconnected from the grid, and a lot of people were affected by this blackout. So that was pretty much like a partial blackout, I can say, if not, because some section of the city was still active. But the biggest problem here is, they were actually quite ready for, or how should I, or they were actually quite prepared for what should be the next steps, and they left no traces of what really happened. So they even did a denial of service attack on the telephone lines as well. So if the system operators wanted to talk to each other, they could not do that. So that was a very well planned cyber attack. And now, as we are moving more into the Powertronics era, you can see that there are a lot of electric vehicles, electric ships, electric aircrafts. And I found out a lot of reports. Of course, these are very few, but if you just take a Google search, you will see that a lot of cyber attacks are actually being interfaced in these systems right now. So the question here is, are we moving into a secure Powertronics era as well? Because we are so much dependent on communication, but then you also have problems there. And this is a latest report from Danish Cyber and Information Security Strategy. Denmark actually acknowledges this threat, as Denmark is one of the leading frontrunners in digitalization in the world. And you can see that the cyber-related crimes are increasing every day in Denmark, so much that it has actually surpassed, the number of burglaries they have right now. So Denmark primarily focuses on 3 trends in digitalization: cybersecurity competences, secure networks, and security by design. This has to be done for every physical system. And this is where we want to understand what could it mean for Powertronics. Now, I think this is the key slide here, how I would link this to firemen. You can see that I describe 2 approaches here. One is a data-driven approach, and one is a model-driven approach. So right now, or before talking to Pedro about this, we were pretty much reliant on this approach. Okay, so this is where you understand the dynamics of the Powertronic converters or the system, how they operate, and you know what fault could do. So any discriminator from fault was identified as a cyber attack, And then we try to understand where this cyber attack is present. So this is the physics-informed detection tool. And then we created an alarm that, okay, a cyber attack has happened and on this signal. And then we move on to the mitigation stage. Another way could be you take a lot of data, you are saving it to the cloud all the time, and you have a very good data set of, let's say, a lot of data for the last 5 years. Now, what you do is you take all the data and then you come up with a data-driven test or data-driven tool, whether it was a cyber attack or fault. And from there, if it was a cyber attack, you could have gone to the detection stage, the mitigation stage, and finally normalcy. But a very interesting problem here is that the smart cyber attacks can also happen in the cloud. If an adversary actually comes in and manipulates some of the data in the cloud, so if you are going to use this data for training or anything else, then you're always going to have false alarms. Okay, and this false alarm, well, it is going to be for the anomaly detection or data-driven detection as well for the cyber attack. Okay, so in this case, you only have one vulnerability, that is the sensing part. But in the data-driven one, you have the sensing part. Maybe they are not so vulnerable, but you always have the cloud part, and they are quite vulnerable. So this is where I think we have some activities with firemen where we are trying to understand, what if this part is attacked? Can we explain the actions of this anomaly detection and the data-driven detection of cyber attacks? And then we are trying to understand if we can combine both these approaches, if we can combine both physics and data to come up with a very reliable approach of cybersecurity for Powertronics systems. So the requirement basically is that cybersecurity solutions for Powertronics needs to be very fast, accurate, and precise. I can say that this can be commonly said for any system, but when I say fast, it's basically few milliseconds. If you do not complete this framework within a few milliseconds, then your system is already lost. All the Powertronic converters have basically triggered the limits of over voltage, over current, relays have operated quickly, and your system is gone. So the power generation is basically shut down because of some cyber attack, and it is not really a real event. So the cybersecurity framework is not very straightforward. You can see you have the anomaly detection stage where you identify whether it was a fault. When I say a fault, it's something, I term it as a natural anomaly, which people know about, let's say sensor faults, grid faults, and all those things. And then there's a protection strategy here. They go towards the defined countermeasures, and then you go towards the normalcy. So this is what has been happening until now, but now there's a new chain. You also have the cyber attack detection stage, if it was a cyber attack, and then you go into the mitigation stage. Now, this chain has to be completed in few milliseconds. That's maybe at best 5 milliseconds or something like that. If you do not complete it, then again, your converters are gone. Strategic formulation of cyber attacks. This is also something we have been working on in Fireman, where we inject false data and try to understand if the cyber attack can be replicated as a fault. In this case, it will actually affect this stage. So if these cyber attacks are modeled as faults and the response of Powertronic converter actually looks like a fault, a real fault, then in this case you will always go in this direction, and that is what the attacker basically would want from you. So cyber attacks are not going to be very obvious. They're not stupid to give you very easy clues that someone is already in your system. So how I understand this is, and this is what I learned from this Ukrainian cyber attack, is that they launch an attack into the system, and they also observe what's going on, what are the voltage limits, line limits, and all those things. So they remain stealth for a very long time, and they observe the normal operation. This is also a key when they try to understand, or if they do not have system information, this is where they actually get to know a lot about your system. Okay, and based on this, if they have some information, whatever this information is, they disorient the system operation later. So if they want to actually have a shutdown, they will target you during the most vulnerable stage. Let's say there's a big event or Christmas or something like this. They will target your system during those days, because they have actually collected a lot of information during this time. So the target is, if there is a smart attack which is initiated, you should actually take it out right there and not wait for this to happen. And this, based on the approaches that have been defined today, they always wait for this to happen and then they actually come up with countermeasures. But what I say is, when you see that there is a smart attack initiated, you trip them right there. But of course, this is not so easy. I mean, there can be very smart cyber attacks and you can get hacked very easily. So of all the cyber attacks that have happened in the power grid, you can, from this report, I found out that 74% of the cyber attacks actually happened in the control layer. So the control layer in Powertronic systems actually needs a lot of attention. So cyber attack detection methods, we have pretty much done it all, but I would like to take this forward, the control theory. We have also done data-driven approaches, signal processing as well, but I would prefer put all my money on control theory, because this is where you know the dynamics, and this is where we are saying that we do not need a lot of information from you. We only need to know, why have you put the Powertronic converter in your system? So basically, if you are putting any converter, we would just ask, why do you need communication for this converter? And based on this, you actually go forward. So if you would like to know more about what we have done, you can refer to our activities from these papers. So based on what I described for this one, third one, I can say that the disagreement index is actually designed based on what your control strategy already was in that system. So we are not trying to change the control strategy that you have for Powertronic converters, because they are already deployed in the field. So if you ask, and this is a very practical discussion happening right now with one of the industry, if you ask them to change the control strategy, they will never do this. So they will always want that you give us some additional monitors and then take it on from there. You find a solution in their existing mechanism. If you ask them to actually come up with a plug and play tool, they are not very open about this, because it's a cybersecurity tool. So they don't really trust you with this new tool or something like that. So based on these requirements, our detection strategy actually ensures that the detection metrics, it does not really require design of an additional observer. So we do not need any observer, which also increases the computational complexity. It does not need any system information. So I don't know how large the system is. I don't have to know the control parameters, the LCL filters, and all those things. So really, we do not need any system information. Historic data, we don't need to know how this converter was operating 5 years ago or 5 days ago. Okay, so it only relies on online data from the system, and it does not also require any additional resources. So we do not go for additional sensors and communication bandwidth. So right now, we are in this anomaly detection stage with Pavel, Alex, Haralampos, Janos, and Pedro, where we collected a lot of data from the test bed, which I will show in the next slides. And now we are trying to study if for different faults and different abnormal events, how this tool actually, how fast can this tool tell us if we have the right theme or not, if we have the right result or not. And now we have the mitigation stage. So you can see when we go towards the mitigation stage, once you have identified which measurement was attacked, you need to stop communicating these attack measurements to other units. So once you find out that this is faulty, you stop the communication of that measurement right there. So because you don't want to use it in your control system anymore. What you do is, if you have an attacked system, and consider this as a multi-agent system where you have multiple agents, and one of the agent is, let's say, attacked. What you need to do is you need to transmit the trustworthy measurements. So what you need to do is put an authentication label here. So an authentication label of false is assigned to the attack measurement and vice versa. So for the measurements which are not attacked, you assign them as true, and one which is attacked, you assign them as false. So you transmit the trustworthy measurements into the attack unit, and using the trustworthy measurements, what you need to do is you have the detection metric, and you need to create some boundaries, that is beta and minus beta. which I have basically shown here. So these are the boundaries, and these boundaries, I mean, these values are very small depending on how much noise you have in your system. And based on these boundaries, if this attack detection matrix actually tries to touch the upper or the lower boundary, it is going to cause triggers here. Based on these triggers, you are basically making another digital signal. And this is quite similar to what you would like to do when the system is operating normally. Okay, so this is a digital replica of the trustworthy signal. And now you replace it with the attack measurement, and then you start transmitting it to other measurements. So in this way, you can see that it heals the system by itself. So you create another new measurement, which is substituted with the attack measurement, and the system can just operate normally, and you can start transmitting them to other converters. So it's quite similar to what I would say is event triggering, except for the fact that event triggering is used for any kind of disturbances. But right now we have made it very specific and just put the presence of attack as one of the defined from the cyber attack detection metrics that I've discussed. It's termed as an event. So if this is an event, you actually are recreating another signal. So if this value is large, then the resolution of the signal will also be bad. But if this signal is very small, if this value is very small, then you can have a very good resolution. So in this way, we are analyzing the stability, the convergence, and all those things. So right now, we haven't taken any data. We haven't used any additional resources, but this can be improved. So a video from our lab where I test this on 2 Powertronic converters and how this works. So I think I can just start here. So I started them, and you can see that 2 converters are sharing currents. And this is the attack vector that I started. They go on to some level. And I start the resilient controller. And you can see that they come back. And when I change the value of attack, you can see that they anyway just push it back. I launched another attack on one of the converters of 15 amps. You can see that it cannot do anything to the system. So even if your IT system is down and is there with some cyber attack element, it cannot affect the physical system, physical distribution system. So I will show you another video where this is more about equal current sharing. So it's more easy. So any load change, it will always share the load equally. And now you can see that I am initiating an attack of 1.5 amps on one of the current. You can see that it anyway comes back. And even though I try to increase the value of attack, it does not affect the system. The system just keeps operating in its own way. So we have discussed about these, strategies in these papers and transactions from Powertronics. So this is the cybersecurity test bed in Aalborg University, where we have 8 silicon carbide converters and then a 45 kVA linear amplifier, where you can model any kind of grid disturbance, power quality measures. It is also used for electrical testing of these converters as well. And this is where you can also have a fault. Okay, so this is something which is new for us, and I would like to test it here. And we have already developed a lot of tools. Not me, actually, it's just Paul and Alex basically doing all the work. And we would like to test it in experimental setup to see if this makes sense or not. And then our end goal is to make this commercial so that Danfoss Vestas can actually use it without requiring a lot of data. So the challenges here would be to understand how much data do we need, because A, the industry does not want to share a lot of data with you because of these issues, cybersecurity issues in the first place. And B is, can we combine physics and data and come up with a very reliable tool? So we also have a PhD course on cybersecurity for microgrids in Aalborg University next year. I also did this course as a summer in the summer school for Pedro, and I think many people came there, and it was excellent having these discussions with them. So now I would like to summarize my presentation. So different cyber attack models, including the models which are replicated as false. So these cyber attacks are introduced into the model, which will look like false. in anomaly detection between cyber attacks and other malfunctioning events, physics-informed cyber attack detection metrics, but we are moving more into the data-driven cyber, explainable machine learning tools using firemen, where we can actually say that, okay, this is a cyber attack and this is a form. So there are two aspects. One will be anomaly detection, and another one would be the cyber attack classification. And then this is the event-driven signal reconstruction. So when we are in this world of, let's say, data-driven or model-driven, I come up with another approach, which is called as objective-oriented. So when I say objective-oriented, you just need to know why are the converters placed in the system with communication integrated into it, because what is the purpose of communication? And you always have to have a system objective for communication. So if that objective is known, we can design this event-driven mitigation and come up with a digital replica of this measurement. It reports a resiliency scale of n-1, and this is the best that has been reported till date for any system, because without using any historic data, I must say, because if, let's say, what this means is, if in a system with n converters, if n-1 converters are attacked, the system can come back to the normalcy. If n converters are attacked, then we cannot ensure normalcy anymore. So it's not 100% resiliency. So, but it's always n-1. Why is it n-1? Is because we only need one converter to transmit trustworthy measurements. So as long as we have that one converter, we can bring the system back to normalcy. So that's why it's n-1. Resilient to noise and feasible for many worst case attack scenarios as well. So this is quite scalable. Computationally simple and easy to deploy. This is something which has given us a lot of advantages, and we are already in talks with Danfoss, who would like to integrate this into their drive systems as well. So yes, that will be the end of my presentation. If you have any questions, I would love to answer them for you. Thank you so much.
Thanks, Subham. I think it was very nice and very, very good presentation. And then, as you mentioned, like you have given the course to us here, and then it was, well, it's very good. And then also really, like, as I mentioned, like, we even discuss about my book and so on. I really get like a very common place and then very clear application. Also, that's like, I think most people from the communication society, or not most, but several people in communication society talk about this type of semantic or goal-oriented communications, and I guess it is still in the same problem as before. And I think what you gave, it's exactly how it should look like. So basically, the cyber physical system that you're looking at give you the semantics. Basically, the power electronics give the meaning of the data, and of course the function to detect anomaly. This is the goal oriented, and then from this I think you can thinking about the best communication system to perform this task given the goal that you need to achieve. But this is like a discussion for different places and so on, but I think this is a very important and very timely discussion for both, at least not both communities, but several communities, like data science community, and then Pavel and Alex are the video programmers, like communication. So how you make this and communication better, for example, event driven, not only like the sampling or acquisition or reconstruction that are mentioned, but also in the communication part, how you design some system to get like this event data. You have also some research in this data imputation that would like being like how to recover missing data, and so I think this is excellent. Like we have so many research ideas to move ahead. So then I think this is excellent. So, but I guess I could not like again not be so short on time. Maybe we can have our short break now. Again, 5 minutes. You can. Is
there a chance to have any questions, Pedro, or not anymore?
Okay, so
if it's possible, maybe but I can send a message to an email to Subham. Maybe that's better.
Yeah, or maybe
it's better.
Maybe you can make a question in like a kind of break. So who wants to go to make some small break, but you can have a question and then like who wants to stay, don't need a break, then stay.
Yeah.
Who wants a
no,
break?
I will send an email. It's better, I guess, for everybody.
Yeah, so or just message here in the chat. So during the Sohan can answer. So that's
okay. Great. Thank you, Subham.
And this is of course.
Thank you.
And yes. I think everyone can. Oh, you see, Sohan's mail is here. So just send the mail. So don't even to ask him.
Yes.
And
just send an email and we can talk.
Yeah, and then we can a lot of collaboration that it's possible in there. And then I think this is great. And then this is the idea to have those workshops. And then it's nice that I see like 50 people. And then as I discussed with Hirle in the previous time, it's very good to have those because usually there is more people here than if you have the workshop in conference and so on. And then it's nice that you can collaborate and make new bridges in research. And then actually, I think this is important because one of the reasons that Sohan is presenting here today is because last time he was here watching some presentations and had ideas of how to use it in power electronics. I guess this is other outcome of our this kind of event. So,
and I think we are on a very good track. Based on all the weekly discussions, I think we have very good results. But I just didn't want to put them all here because it will be highly technical and in 30 minutes how much can you capture, but I just wanted to give an overview of what our challenges are. I guess some already know, but a lot of people just don't know about the system. So I just introduced them to the system a bit.
That's very good. So I think that's so. Let's have this short break and then we can, I don't know, Pavel is going to present something or no, Pavel?
Well, I don't think so. Well, I don't have prepared anything, so I think that's
okay. That's just to be sure, because like in the end, like I thought that like I would like to present, but I think Subham covered.
I was hoping to have some preliminary results by now, but unfortunately I got stuck in multiple ideas and not finishing any of them. And of course, I'm sorry for that. But
no problem. Next workshop, you're already the presenter in that. So
I have no problem with that.
That's good. No, thanks, Pavel. So let's have this break and then let's come back at let's try to come back at 3, and then a very quick break, and then Jesse can start like upload the presentation, and so then you can move ahead on time. So let's have this short break now.
All right.